Hello, welcome to Team 174's final project presentation. I'm Webb Bass, and our topic was music genre classification using spectrograms. So the dataset we chose is called the GTZN dataset, music genre classification. This is from Kaggle. The dataset is 10 genres, 100 samples per genre, and each sample has its own MEL spectrogram that was included in the dataset. Each sample is a 30-second WAV file, and to the right you can see all the categories of music that we have, or all the genres of music: blues, classical, country, disco, hip-hop, jazz, metal, pop, reggae, and rock. Also included in the dataset are a 30-second and a 3-second feature CSV. So this has features for all the samples, and the 3-second feature CSV is actually each 30-second sample split into 10 3-second samples. That will be used later. For our pre-processing, since we're using spectrograms, we looked at the provided one, and we kind of noticed there was a lot of white space around it, and we were a bit worried that would cause some unwanted noise in our model. And so we created a Python script to remove all the white space. And by the way, this is blues 0.wav, that's the sample. So we cropped it, and that actually lost some data by doing that, and we ended up losing a couple of our samples that way. So that was not an option. And in the end, we actually wanted to create something. So we ended up creating our own spectrograms using the WAV files. So for our architecture, we're using a 4-layer CNN plus a 2 or 3-layer FCN. That is variant. The CNN contains convolutional layers, an activation function, pooling layers, and normalization layers. The FCN contains flattening layers, dense layers, and output layers. Our hyperparameters were tuned using the Optuna framework, and that was done remotely. For our performance metrics, these are the top 3 models that we received through the tuning, and our highest has an accuracy of 71%, which is a huge increase from our baseline of around 43%. Some observations and final notes. So I'm actually going to go back. So as you can see on the leftmost model, we have very high accuracies in classical and very low accuracies in things such as rock and even country. This may indicate that we need feature differentiation. This model was also built from scratch, so you can compare it against other pre-trained models, and you'll kind of gain insight on how it actually is a very good model. And again, optimized configuration. So we used Optuna for our tuning, and that also avoids specific dropout rates, weight decay, kernel sizes in order to get our best model performance. So going on in the future, some things we want to maybe implement are a pre-trained model or transfer learning, implementation of a time domain algorithm such as long short-term memory or LSTM network, and better feature extraction of the spectrograms. So we could definitely get some better spectrograms going, I think, and possibly even better features out of them. Or we use a model that takes longer to train but results in less overfitting, or like a more robust model, obviously. Currently, right now, we are splitting the audio into 3-second samples in order, like, quote unquote, more data. So basically, like I mentioned earlier in the presentation, splitting each 30-second sample into 10 equal 3-second samples. And so right now we're working on creating the spectrograms for that, and we'll see if that increases our accuracy even more. And that is it. Thank you for attending.